Understanding sine and cosine through geometry. If we take a point M on the unit circle, and this point is determined by an angle theta measured from the horizontal axis, then the cosine and the sine are simply the coordinates of this point M. We will develop this concept together, step by step. Let us first look at the projection of point M onto the horizontal axis, that is, the x-axis. From point M, we project vertically down to the x-axis. This gives a projection point. The signed distance from the origin O to this projection point, measured along the x-axis, is exactly the cosine of the angle theta. This signed distance can be positive or negative. If the projection of point M lies on the positive side of the x-axis, then the cosine is positive. If it lies on the negative side, then the cosine is negative. In other words, the cosine of theta represents the horizontal coordinate of point M. Let us now look at the projection of point M onto the vertical axis, that is, the y-axis. From point M, we project horizontally to the y-axis. The signed distance from the origin O to this projection point, measured along the y-axis, is the sine of the angle theta. Here again, this signed distance can be positive or negative. If the projection of point M is above the origin, the sine is positive. If it is below the origin, the sine is negative. Thus, the sine of theta corresponds to the vertical coordinate of point M. Why are cosine and sine bounded between -1 and 1? We know that cosine and sine are bounded between -1 and 1. In other words, for any angle theta, both cosine theta and sine theta belong to the interval -1 to 1. The question is, why? Let us look at the unit circle. On this circle, the radius always has a length equal to 1. The point M moves along this circle, but it can never move away from it. The cosine represents the projection of point M onto the horizontal axis. The distance to this projection can never exceed the radius. Therefore, the cosine can never be greater than 1. And when the projection of point M lies on the negative side of the x-axis, the cosine becomes negative, but it cannot be less than -1. In the same way, the sine represents the projection of point M onto the vertical axis. This projection is also limited by the radius. Therefore, the sine can never be greater than 1, nor can it be less than -1 when the projection is on the negative side. Let us now look at a few examples to better understand this. Here the angle theta is equal to 0. The point M lies on the positive horizontal axis. We then observe that the cosine of theta is equal to 1, which represents, as you can see, the full radius, and the sine of theta is equal to 0. Here the angle theta is equal to pi over 6, so the cosine of theta is then equal to square root of 3 over 2, and the sine of theta is equal to 1/2, which represents half the radius along the vertical axis. Now theta is equal to pi over 3. We find that the cosine of theta is 1/2, which corresponds to half the radius along the horizontal axis. And the sine of theta is equal to square root of 3 over 2, which is a larger vertical projection. Here theta is equal to pi over 2. As you can see, the cosine of theta is equal to 0 because the horizontal projection is 0. But the sine of theta is equal to 1, which corresponds to the full radius along the vertical axis. Beyond this point, the cosine becomes negative. Here the angle theta is equal to pi. The cosine of theta is then equal to -1, which corresponds to the maximum projection in the negative direction of the x-axis. And the sine of theta is equal to 0. Finally, after one complete rotation, theta is equal to 2 pi. We return to the starting point. the cosine of theta is equal to 1, and the sine of theta is equal to 0. Have you noticed something important here? Whether we take theta equal to 0 or theta equal to 2 pi, we obtain exactly the same values. The cosine of theta is equal to 1, and the sine of theta is equal to 0. In other words, the cosine of 2 pi is equal to the cosine of 0, and the sine of 2 pi is equal to the sine of 0. We then arrive at a very important property. The cosine of theta plus 2 pi is equal to the cosine of theta, and the sine of theta plus 2 pi is equal to the sine of theta. And this remains true if we add several complete rotations. More generally, we can write the cosine of theta plus 2k pi is equal to the cosine of theta, and the sine of theta plus 2k pi is equal to the sine of theta, where k is an integer. Indeed, if we take an angle theta and add, in the positive or negative direction, one or several complete rotations, 2 pi, 4 pi, 6 pi, or even 100 pi, we always end up at the same point on the circle. And since the point is the same, the coordinates are the same. Therefore, cosine and sine keep exactly the same values. On the unit circle, cosine and sine depend only on the position of the point, not on the number of rotations performed.